Hello, everyone, and thank you for joining us today for another A Spotlight presentation. My name is Rouzbeh Afrasiabi, and I'll be your host. Today, we have Justin Sybrandt, who is a PhD at the School of Computing, Clemson University. Today, he will be talking about his recent work titled Hypothesis Generation with Agatha, Accelerates Scientific Discovery with Deep Learning. With that, and without further ado, I pass the mic to Justin.
Thank you so much. I'm so excited to be here. Thank you for giving me the opportunity to talk about all of the work we've done in hypothesis generation and deep learning. So without further ado, let's get into it. I want to motivate the discussion we're about to have with this problem of drug discovery. So a lot of our work focuses in the biomedical sciences. And when you're trying to find a new drug treatment, you start with the disease you'd like to treat, and you think of maybe 10,000 different substances, genes, or different prior drugs that you're interested in exploring for this application. But you need to really quickly winnow that down to about a dozen candidates that you're going to really prioritize for future research. And ultimately, you can only afford to conduct 1 or 2 human trials. This process is really time-consuming, expensive, and risky. In 2018, Pfizer discarded $1.2 billion of Alzheimer's research because something in this pipeline didn't work out. So it's the goal of hypothesis generation systems to get more information cheaper and earlier in pipelines like this, so we can ultimately accelerate research. Why do we think we can do that? Well, PubMed is a repository of practically all English language biomedical literature, at least for the last couple of decades. And its backend, Medline, is something that we have free access to. It contains nearly 30 million biomedical papers, titles and abstracts and associated metadata. And it's increasing at a rate of about 1 million papers per year. I worked this out to be about a new paper every 35 seconds. And as a result, it's really easy to have missed connections or auxiliary information to your research project that you might have not found in this kind of flood of available research. This opens the door for the ability for machine learning systems to help provide more information to decision makers that they might have missed. One particular missed connection that's interesting in this field is the connection between fish oil and Raynaud's syndrome. This was like the foundationary result that started off hypothesis generation in the mid-'80s. And it's a really good example of what we're looking for. So there were papers that mentioned fish oil and blood viscosity in their titles, and there were other papers that mentioned Raynaud's syndrome and blood viscosity in their titles. And by a simple title keyword overlap strategy, the Arrowsmith system was able to find this ABC connection, which was implicitly published already in the medical literature, but until it is explicitly known in the head of an actual scientist, we can't act on it. Now that this machine learning system has identified this connection, fish oil is actually an accepted treatment for Raynaud's syndrome. Now, clearly, machine learning has gone a long ways since the mid-'80s. I actually just defended my dissertation last Thursday, focused a lot on different hypothesis generation techniques. And we've, prior to the Agatha system, done a lot of work with this system called Molier, which I'm just going to introduce because it forms an interesting baseline for what we're about to talk about. And I think it contextualizes some of the decisions we made in this Agatha paper. Molier takes the existing wealth of biomedical information and uses it to build this big semantic network, where each entity, drug, disease, gene, and paper all form different nodes. A user who's interested in a particular relationship between 2 nodes of interest can specify that to the Molier system, and the system will use a shortest path query, kind of basic graph analysis, to find a region in that network we care about. We can analyze the papers that occur in that region to find things like the topic models that describe the discussion that people have been having about your relationship of interest. And we've proposed a number of different heuristic-based ranking techniques to automatically quantify the plausibility of these types of connections. Now, Molier was a really good benchmark, both in hypothesis generation and for me, kind of learning this process over the last 4 years. But it has some limitations. It took a couple minutes for each query, and when we extended that to like full text papers and another work, it took hours per query. And of course, the ranking I just described used a lot of heuristics. That said, we had some really early success with Molier, which in my opinion demonstrate the amount of progress that there is still to be made in hypothesis generation. So we were interested in HIV-associated dementia, and we ranked 40,000 genes that could be found both in the human body and in the Molier semantic network. And we prioritized those genes based on their plausibility to this particular disease based on our heuristics. Well, it turns out the gene DDX3 was ranked pretty highly, and our medical collaborators thought that this was peculiar. They weren't expecting to see it. So we ran laboratory tests and actually found that inhibiting this gene can be a potential treatment target for HIV-associated dementia. So that's what we could do with some, at this point, out-of-date, machine learning moves really fast, some out-of-date techniques and some heuristic-based ranking. And that's really valuable, but it also demonstrates to me that there's so much more room to grow and a lot of ways that we can challenge those early assumptions to hopefully get better performance. And we're going to see that with Agatha. Agatha is a new hypothesis generation system that we really just finished the paper on a couple months ago. It's going to take all of the existing biomedical literature and construct a really large semantic network with some interesting new properties. And we can train a data-driven ranking criteria to both replace those heuristics I just talked about and gain new information directly from that semantic graph, because we're going to take advantage of graph embeddings rather than use some like topic modeling intermediate that I've just discussed. And ultimately, because we're doing this deep learning-based inference and replacing a lot of graph analytics, we're going to be able to perform hundreds of queries per minute rather than one query in a number of minutes. So without further ado, let's get into the Agatha system. We have a really complicated pipeline. I can get into tons more details on this, but a lot of the fine nitty-gritties are going to stay in the paper. But let's walk through what we've got. The Medline data set is what we've been talking about. It's got about 30 million abstracts. And we want to extract the most granular form of information from each abstract, which we're going to represent as each sentence. So we split out each sentence so that each can be treated as a unique element in our network. But within the sentence, there's a bunch of elements of interest. These are going to be lemmas, so stemmed keywords associated with parts of speech. And we can combine lemmas together into entities and n-grams using a combination of existing named entity recognition tools and some simple rules-based n-gram mining. So we restrict some rules about how the parts of speech interact on n-grams, and we get all frequent n-grams from 2 to 4. We can combine that with this extra data set, which is parsed by SemRep. It parses the same abstracts, but finds all subject-verb-object statements that were made within our whole set of 30 million abstracts. For each statement, we not only have the original text associated with the subjects and objects, but we can also represent these as a set of coded terms. So all of the biomedical synonyms are going to be unified under a certain code. This is backed by the Unified Medical Language System, but it's important to note that we're actually just taking the quality terms produced by the SemRep method rather than relying directly on what we find to be a slightly noisier, much larger data set. Anyways, all of that's going to be merged together into this very large semantic graph, which we're going to embed and use to train our model. So let's explore the semantic graph for a second. What I'm showing you on the right is the graph schema. So each node represents a type, and the edges represent different types of connections. We see that we have all of our sentences, and each component of a sentence is given an edge to all of the sentences that use that component. For instance, we have the word cancer as a noun showing up in that set of lemmas, and that's going to be connected to every sentence that mentions the noun cancer. Longer phrases or entities are going to have different nodes also connected to the same sentence, and those both metadata terms and those synonyms parsed out by our predicate set are going to be given codes that, again, occur as different types of nodes. The set of predicates, additionally, becomes a new layer in our network and is given both edges to all of the sentences that use those predicates and all of the elementary components that are comprised within. Now, the sentences are particularly interesting. We make an edge between two sentences within the same abstract that are adjacent to each other. And we induce a nearest neighbors network on Sybrandt sentence embeddings in order to make it, include edges where two sentences are given an edge if they contain semantically relevant content. Now, this network's really large. In the most up-to-date version that we've been processing that we have yet to release publicly, the 2020 release, we have 270 million nodes and about 13 billion edges. The version that we're going to do our analysis on was trained using data up to 2015. That has 188 million nodes, something like 12 billion edges. So either way you look at it, this is a big data problem and is going to need some sophisticated methods to help us understand. But we're going to take all of that information from our semantic graph, and we're going to use it to build this learned ranking criteria. And we're going to use a deep learning transformer encoder model in order to produce this ranking. Now, if anybody has been following recent text mining, particularly the BERT model, this transformer encoder should feel familiar to you, but I want to bend some assumptions you might have. We are not doing text processing with this model. We're instead going to be looking at sets of node embeddings and combining the intuitions from that set of node embeddings through the series of all pairs comparisons that we'll talk about in a second, in order to produce a ranking criteria. And unlike some existing text models, we're going to train this directly from our graph embeddings. There's no pre-training component or transfer learning component that you might be familiar with. So let's dive into the transformer encoder, starting with our objective that we're going to optimize. And we're going to work our way backwards through the model, because I find it most intuitive to start at the goal and see how we get there. So I mentioned we want to learn a ranking criteria directly from our data. We're going to minimize margin ranking loss in order to do so. And let's walk through what we're doing. This is the loss associated with a particular alpha-beta connection in our network. I mentioned those predicates, the subject, verb, object statements. Well, for each statement in the network, we're going to formulate the alpha-beta connections among each of these predicates as different training examples. So the loss associated with a particular existing connection between alpha and beta is going to be dependent on the positive formulation of that alpha and beta as compared to a large number of negative samples. This negative sampling should be familiar to people who have done graph embedding models, and I'll explain it in more detail in a second. But ultimately, we're going to minimize margin ranking loss. That means the model output corresponding to a positive formulation needs to be at least some amount larger than all negative formulations. So here we're going to compare the single alpha beta model output to about 50 different bad outputs. And this is what lets us learn our ranking criteria directly from our data. I'll talk about what each—
Sorry, Justin.
Yep.
There's a question online. They're asking, they're not sure what you mean by ranking. What are you ranking?
Oh, yes. Okay. So the end goal of this model, so the end goal of this model is for the user to supply two keywords that they're interested in, maybe a gene and a disease. And we want to assign a numeric score to that question that correlates with the plausibility that if you were to actually do research on that connection, you would find something valuable. Now, this is a really hard number to come up with. And we're going to see how we can validate this number in a little bit. But our goal here is to look at pretty much our set of existing training data and learn some function that, given our objects of interest, we can assign a numeric value such that the ones that we see in our training set are above those that would be randomly sampled outside of our training set. And in the real world, I mentioned drug discovery at the beginning of this talk. You might apply this ranking by having your set of 10,000 different potential targets you're interested in doing further research on, and using this particular ranking criteria to help you make decisions about which of your targets are going to get higher priority. Cool. Does that make sense?
Yeah, thank you so much.
Great. Okay. Hopefully I wasn't too verbose also. Okay, so we just talked about margin ranking loss. We're going to try to make it so that positive samples are above negative samples. So let's dig into what those are. A positive sample is formulated as follows. We have alpha and beta, which are going to correspond to two elements of interest that we have a known connection between. And we have a bunch of gammas. These gammas are going to correspond to prior knowledge associated with both alpha and beta. Now, it doesn't make sense to show the model a shared neighbor of both alpha and beta. For instance, if there's an obvious relationship between the two that has already been published and exists in our network. We do not want the model to learn that trivial relationship, so instead, we sample these gammas from the disjoint sets of neighborhoods. So here, capital gamma represents the neighborhood of both alpha or beta, and we take the disjoint subsets in order to get our prior knowledge.
Sorry, Justin. In regards to the ranking system, they're saying they're asking if you can provide examples so that they can understand better what you mean by ranking.
Yeah, we're going to see a little bit more at the end of the talk, but let me give you an example. Well, actually, we can take a little bit of a step backwards to this example. So the Molier system, we did a lot of work in order to get a ranking, and we applied this ranking in the real world. We were interested in a disease, HIV-associated dementia, and we wanted to know which genes in the human body might be most related to that disease. So this is a ranking problem because we would like, out of our set of 40,000 genes, to order them in such a way that the genes that show at the top of that ordering are the most likely, from the perspective of our system, to be useful for treating this particular disease. So in our laboratory experiments with this older system, we actually found that our ranking was able to uncover DDX3, which was highly ranked and led to an actual medical discovery. You could see this in many different applications. That makes sense, hopefully?
Yeah, it makes sense to me. I think that they got their answer. Thank you.
Cool. Okay. Great. Let's jump back to where we are. We're formulating our loss function, margin ranking loss. We've got a positive example. It's got the data we care about, alpha and beta, as well as prior knowledge that doesn't give away the game. We need to compare that to different negative examples. And I mentioned there were two types. There's negative scrambles and swaps. The scrambles are easy for the model to distinguish from positive examples because the negative scrambles correlate to malformed input. The model should learn that this example doesn't make any sense and downrank it. This doesn't really help us learn anything very useful, but it's really important for the early convergence of our model to get the training going in the right direction. So we form the sample to be X and Y, such that there's no known relationship between X and Y. And we sample gammas randomly. There's no relationship to the prior knowledge that we're sampling and the information we'd like to uncover. So the model should learn that this doesn't make any sense, rank it low. The negative swap is harder for the model to pick up. And this is going to require that our Agatha model actually learn something that's domain relevant. Again, we have X and Y such that there's no known relationship between X and Y. However, we sample the gammas, the prior knowledge, appropriately. The model does actually see all the information it needs about X and all the information it needs about Y. And it needs to know that there just doesn't make sense to put a connection here. So this requires a bit more domain information, and this is our harder negative sample to compare against. So this is the mechanism to which we learn a ranking criteria directly from the data. So now we just need to explore the model that we use to create that numeric result for each predicate. For that, we use a transformer encoder. Now, this model should feel familiar to people who have followed recent text mining. If you haven't, we'll summarize it. So script H is the ranking criteria associated with a particular input. So that's a value in 0, 1, because what we're going to do is take the average output embedding of our model, project it to the unit interval with a combination of a learned weight and the sigmoid function. Let me take a step backwards. The transformer encoder is fundamentally a method that takes n input embeddings and performs an all pairs comparison to produce n output embeddings. This allows us to get really fine-tuned relationships between all of the elements that we've sampled, which is why we've selected this model formulation. But once we have our n output embeddings at the last step of the transformer encoder, we ultimately just need one number. For that, we're going to average all of our output embeddings together, here that's script m, and then project that down to the unit interval. Okay, so now we just need to understand the encoder block. The encoder block has some residual connections, some normalization, and a feed forward in the middle. This is pretty standard, and you see the formulation on the left-hand side. The main mechanism that gives us that all pairs comparison comes from the multi-headed self-attention layer. Let's dive into that. I mentioned that attention is this all pairs comparison. It is a learned weighted average over your inputs, and it's described as such. We have this attention function with three matrices, Q, K, and V. Each of these are stacked matrices, so each column corresponds to one of our embeddings. And we're going to see that the Ks and Qs form this key value relationship. So if the Ks and Qs line up, then we're going to assign a higher weight to the particular embedding in V. So this is how we learn our weighted average. And this is the attention mechanism. But we have multi-headed self-attention. Well, it's multi-headed because we're going to compute the attention mechanism multiple times. And it's self-attention because we're going to derive Q, K, and V all from the same set of input embeddings. So this is the mechanism to which we have our set of input embeddings. We're going to learn an all pairs comparison between them and produce a set of output embeddings such that each output embedding is related to all input embeddings. Okay, so that's the transformer encoder out of the way. All we need now are our initial set of input embeddings for us to understand how the model gets access to the content of its semantic graph. For that, we need a really high-performance graph embedding technique, which we're going to use the PyTorch Big Graph distributed graph embedding. This allows us to take something like 400 cores across 20 machines and run our graph embedding for 3 whole days on our 188 million node network. And we're going to optimize the following function as a pre-processing step to training the Agatha model. So we're going to optimize softmax loss, where each edge in our network, that Si and J, is going to be compared to 100 negative samples of edges that do not exist in the network. And this S, which I'm going to define on the next slide, is our estimated similarity function between 2 nodes in our network. And in order to learn this S, we're going to have to find embeddings that fit a certain property so that we can uncover the edges of our network and prioritize those above those negative samples. So what do we choose to fit? We use a bias transform dot product of our semantic graph. This is actually kind of standard for heterogeneous graphs of our size, but we'll walk through it in a second. It's transformed, let's start with that, because our nodes are of different types. So when we have a similarity between nodes I and J, we're going to need embeddings for both of those. But we're going to need to transform those embeddings based on the types of nodes we're looking at. The types come from this capital T term. So our semantic graph has a bunch of types of nodes. For instance, the node sentence and n-gram. When we have an edge between a sentence and an n-gram, we can look up a unique transformation for that type. And we're going to add that transformation to the right-hand side of our particular edge. So note that while our semantic graph is undirected, we're going to actually make 2 different directed transformations for every type of edge in our network. Okay, so that's the transformation. We're adding some learned vector to the right-hand side. Now we're going to perform the dot product for almost all of the embedding. We're going to omit the first dimension and simply do a pairwise multiplication and sum for the rest of the embeddings. And that first dimension is our bias. Some nodes in our network simply are more popular than others. For instance, the node that corresponds to Cancer is going to be given new edges all the time, and a node that's corresponding to a particular gene name that might be understudied is simply going to be less studied. This is best encoded as a bias, which we reserve the first dimension of our embedding to encode. Okay, so that's the way in which we get our initial graph embeddings. Our initial graph embeddings act as the first set of inputs to the Agatha model and give us kind of a baseline of biomedical knowledge, which we learned as a pre-processing step. We then perform multi-headed self-attention to learn a single representation for the full predicate, and then that representation can allow us to get a single number corresponding to the plausibility of that predicate as fit by margin ranking loss. Great. So now we just need to know whether or not all that work we did put us in the right direction. So for that, we need to perform some validation. Oh, is there a question? I saw you unmute for a second.
If I can interrupt you for 1 second. Sure. One question that we had online was that since you're using a transformer network, did you test if just using text compared to using graphs, if there was how much improvement you would see? or if you actually tested this.
So interestingly, I worked on two papers at the same time. One was this Agatha paper. The other was a transformer-based text generation paper. And our idea was to explore whether or not you could use predictive text to help understand your hypotheses. We find that the predictive text is really good at giving a potential description of the thing you're looking for, but we find that your precision on uncovering particular keywords isn't as high. So for instance, when you see GPT-2 being used to predict certain particular relationships, so there's a really interesting paper about using text as a knowledge base. One, they trained on like a much larger data set, which is like the whole internet and a bunch of English language sources. And then they formulate particular questions in natural language and use the model to predict what the next word in that question might be. The reason this works is because there's enough people asking regular English questions online for the model to get a sense to how to perform this question answering. It is not obvious to me how to modify the text that we see written in abstracts, which is very summarization based, doesn't have a lot of question answering components, and use that to get a high quality hypothesis generation ranking score. I'm not saying you couldn't do it. I'd be very interested to see that paper. But we find that you kind of want this more graph focused ranking measure that we can learn a bit more directly. Hopefully that answers it. Again, I hope I wasn't too verbose.
Yeah, I think that the question is a bit different than how I stated it. They're saying, well, give me one second. They say you don't have to use the text generation kind of scenario. If the goal is ranking, can't you use something like a Siamese net to achieve that?
Okay. Now, my answer to this question is going to be dependent on whether or not I remember what a Siamese net is appropriately.
No, Siamese net is just it's like a way for you to compare two texts. So it categorizes it. You can easily figure out like the difference between two texts. But in regards to their question, they're saying, but you don't have to use the text generation kind of scenario if the goal is ranking. Can't you use something like a Siamese net to achieve that?
Okay. I certainly believe that there are many different formulations than the one that we've presented that could have some really interesting results. The reason we've gone with this graph-based method over something that might just compare similarities of a plausible text versus the data set of existing text, which I think is what we're getting at here, has to do with a combination of the noise in existing biomedical literature and a lack of, I'm going to say, higher order domain knowledge that you might lose if you're just looking at statements. For instance, if I made the statement like gene A has a inverse relationship to this particular disease, and I formulated that as a statement that should look like something you'd find in a medical abstract, and compared its similarity to my data set of existing text, I think that you could certainly uncover something really useful that feels like a more advanced version of that ABC model we talked about at the very beginning of that talk, or this talk, and surely that had some interesting results. But I think what you would lose is the higher order associations that you would never find in one particular text. For that, I want to explore this more global structure of biomedical information. And I find that this graph embedding approach gives us some really interesting ways to understand two pieces of information that have never been spoken about in the same context that actually have a lot to do with each other.
Yeah, I think like based on the question that they're asking, the Siamese network is not going to really provide you with the connections that you need for creating a hypothesis. That's my understanding. So I totally agree with your answer. Let me see if they seems like they're asking more questions. I'm sure graph is better. That's what they're saying. I'm just curious about how much.
Oh, yeah. I'm curious too. We have not done an experience. So we're going to talk about validation in a second. We're going to compare our graph embedding based technique to the topic modeling technique that I talked about with Molier. Maybe this will become a little bit clearer in a couple of slides. I'd be very happy to keep talking about this after we go through validation. So one step backwards. How do we know if we've done a good job? Hypothesis systems are really hard to validate because our goal is to find novel information that is unknown to even us designing the system. So is the system making a choice that's wrong or making a choice that we just don't expect? In order to validate existing hypothesis generation systems, the field as a whole has taken a lot of what I feel to be stopgap measures on the way to some bronze standard that we can all agree on, because it's really hard to get a gold standard. So let's talk about that. Papers as published as late as last year are validating themselves by replicating about half a dozen experiments from that old Aerosmith system that was published in the 80s and did experiments up through the 90s. That clearly doesn't scale, and it's very qualitative how you choose to interpret your method's results in repredicting this small set of experiments. If you have a particular domain of interest, so I've seen some papers focus just on genes and diseases, you can handcraft some statistical analysis and try to have a bit better validation criteria, but you're going to be limited to that domain that you've handcrafted. Agatha is intended to be a general purpose hypothesis generation system, and we don't have the same luxury of these small scale statistics or small scale data sets. What a lot of people do is take expert help in order to interpret and analyze their data. That's what we did in the beginning with Molier. And that's really useful for seeing that your system's going in the right direction, but you can't really assign a number to system performance. And the ultimate gold standard is for your system to output something and for somebody to find that result in a laboratory. We got to that point with Molier. We're not yet at that point with Agatha. It's a very expensive, time-consuming process that has a ton of bias because you're limited to searching for things that your collaborators care about. And so this is the state of the art in hypothesis generation. We wrote a whole paper 2 years ago trying to push that forward, and it's starting to catch on. Wherein we're going to perform a larger scale validation by generating a bunch of recent hypotheses that have been published and trying to repredict them out using a ranking method given historical text. Let's dive into that for a second, because it's how we're going to begin to quantify Agatha performance. So we mentioned those predicates. The predicates are subject, verb, object statements, and they're added all the time. The plot on the right shows new subject, verb, object statements that have never been published before per year. So the number of new ones per year. And we see that every year, more people are putting more new ideas into our Medline data set than prior years. So we believe we can scale this into the future. What we can do is we can take a temporal-based holdout. In our experiments, we took 2015, and we trained the model on all data published prior to 2015. And we use that information to try to predict those new connections that had not yet been introduced in our training data that were plausible in modern times. So it's a validation-based holdout. We're comparing our recently published predicates versus a equal-sized set of randomly sampled predicates that have never been connected. So when we do that at scale, we can start to do a basic ranking and understand the overall system performance numerically, even though it's not a gold standard. Clearly, there's some flaws to this. I mentioned that we have a balanced training or a balanced test set. We're going to bend that in a second, but we got to start with our Molier baseline as a key point of comparison. So here's what we did with Molier. Again, in 2018, we explored different ways you could formulate Molier using different input text. We showed a range of performance results using different numbers of abstracts and types of papers. So in this paper, like in this work, we compared the Molier trained on abstracts versus Molier trained on full text. We showed an improvement in full text, but that 10% improvement in quality came at a really high runtime cost. And we were very interested to continue to explore our validation method on Agatha. So does our ranking criteria really outperform the heuristics that we proposed in prior work? The answer is yes. So the new bar at 0.9 is Agatha ranking performance on the exact same training data as the Molier system with 100% of Medline. So we see an increase in performance quality from 0.71 to 0.90. That increase in quality is more than using full text papers in the context of Molier, and we decrease runtime. So now we can do hundreds of queries per minute rather than one query in a couple of minutes or a query per hour in the case of full text. So this shows us the added benefit of looking at the semantic graph directly rather than just looking at textual features. And because we've added performance, we can push this validation method a bit further. We want to make it so that our negative samples feel the same as our positive samples. For that, we're going to focus in biomedical subdomains. So we're going to only look at particular types of relationships. And we're going to look at all pairs of potential comparisons within that subdomain in order to try to recommend new fruitful research directions that, of course, have been published after our training set. Let me depict this for a second. I think it's easier to see. Within a particular subdomain, for instance, between genes and diseases, we can find the 100 most popular new connections. So these are the connections that have occurred in the most papers after 2015. And we have 100 positive examples. We can get 10,000 potential examples by doing an all pairs comparisons between all genes and all diseases among that top set. So this means every gene disease connection is firstly a gene disease connection and not just a random sample from the whole data set. And two, occur between two very popular nodes. So the negative samples feel very similar to the positive samples, and we have a very imbalanced data set because we're only going to have 100 good examples and we're going to have something like 10,000 bad examples. Okay, we now look at 20 different popular subdomains in medicine. The full results are in the paper. I'm just going to show a couple here. Our best performing method is the comparison between gene to cell function. For this, we see when trying to recommend the top 100 predicates within gene to cell function comparisons, we get an area under the precision recall curve of 0.44, which is high for an imbalanced data problem like ours. And we see that our highest recommended result is a positive example, and that half of our top 10 are positive. Additionally, if you decompose this into 100 gene versus all cell function queries, so you're doing a cell function recommendation per gene, you expect to see the positive result recovered in the first 2 in all of these rankings. We think this is a really powerful result that shows our ability to take our broad Agatha understanding and apply it to a particular subdomain. We see a similar exploration in gene to neoplastic process and 18 other subdomains, not all having to do with genes, of course. Full results of that are in the paper. So we're coming towards the end of the talk. I want to show that we've done a lot of work to make the Agatha system very usable. The 2015 version of the model with all the data you need to run can be downloaded. I think it's only something like 30 gigs. You can run the model on your own hypothesis queries in about 6 lines of code. And so in summary, that's the Agatha model. It's a deep learning approach to learn our ranking criteria to help accelerate scientific discovery. And here's some contact information if you'd like to follow up. I am more than happy to talk about this. And now we can open it up for as many detailed questions as we'd like.
Thank you so much, Justin, for your wonderful talk. Let's see if we have questions online. It's all praise. They're thanking you for your wonderful presentation. Let's see if
thank you for listening.
Let's see. So one question that they're asking is, what does the input look like? I think that it's a good idea to just give them an example of input and output.
Okay.
So that they can understand how the process works.
So if you're, I'll be like very literal. So here's the Python interface. If you're a doctor, you're probably familiar with PubMed, and you're familiar with things like mesh subject headings. and there's additional headings provided by UMLS. The way our system works as currently formulated for the analysis we've performed is your input to our model is 2 terms, or a list of terms. Here I show that we've got the term corresponding to cancer and the term corresponding to tobacco. If you wanted to do an all pairs connection, you might, iterate sets of lists in order to produce a really long set of pairs of inputs. Behind the scenes, we're going to look at our semantic network and find a set of prior knowledge associated with each of your terms, and we're going to randomly sample that at runtime. And we're going to look up for each of those terms we've identified from the network. We're going to look up graph embeddings from our pre-trained Agatha semantic graph embedding. All of that is going to be concatenated together to a sequence of inputs where we've got the 2 terms and the set of predicates associated with your 2 terms. And each of your queries is treated independently. Then we do the whole attention ranking mechanism to make all pairs comparisons out of what you've provided. And the output is a number. It's kind of important to note that our number output, you could obviously formulate it into classification once you set a threshold, but our analysis is just looking at recommendations. So we actually don't set a threshold. Therefore, the number you see, this 0.78, is useful for relative measures and not so useful for classification, at least from our perspective. So here we see that there's a 0.78 associated with tobacco and cancer. Now, if you compared this to tobacco and something unrelated, you would expect to see a value of like 0.2. This is just from my empirical, having run the system a lot. And you would then sort your pairs by the output ranking in order to get a sense for what's interesting.
Thank you so much. So in this example, you're using 2 keywords. Would it be possible to feed the model 2 abstracts?
Absolutely. It would just require a little change in formulation to how we build our training data.
Okay, so it requires pre-processing before you feed that. You're going to turn them into keywords before you feed them into the model.
Pretty much.
Okay.
If you remember our training formulation, we're looking at those alpha-beta relationships across the set of predicates. This is, of course, because predicates give us such an easy way to look at the existing connections in literature. Mm-hmm. And because our existing validation measures and other people's validation measures are typically all defined on these sets of predicates, so we want to stick with the prior work. With a little bit of engineering, you could reformulate our alpha beta positive samples to be any nodes in our network. Mm-hmm. So yeah, that's an engineering extension of this.
Okay, so going back to the number that we get from the model, mm-hmm. How do you use this number?
So we typically use this to rank results. It makes a little less sense in a particular pair because what is 0.78? That doesn't mean anything. So what we would normally do, for instance, is if we were looking at all potential connections to tobacco, we could have 1,000 different, other like left-hand sides. And you would then perform some ordering and maybe take the top 10. So in that way, you're using our ranking criteria as a recommendation system. Now, it doesn't have to be a recommendation system. One thing that we've been looking into is across our validation, trying to look at our PR curves and pick a tolerance level we feel that we can justify. We haven't released any numbers for that because I think it varies based on the finicky training of any machine learning model. So with your set of prior knowledge, you might pick that a value of like 0.6 gives you a precision of like 0.5. And then you might use this as a classifier with some known parameters. But I'm at least of the opinion that providing a ranking criteria is the most fundamental thing our model can do. And a ranking criteria so directly becomes a recommendation system or a classifier that it's up to you.
Okay, that's great. They're asking, where does the ground truth for the pairs come from?
Okay, so that jumps back a little bit in the talk. There's a data set, or there's a tool called Symrandt, and it has parsed every sentence in Medline to produce subject-verb-object statements among the set of coded terms. So this is not a ground truth in the sense that no human has annotated this, but it is, well, it's kind of the best we've got, and it scales to our whole data set. So what we do is we take all pairs produced by the subject-object relationships across SemRep, and what we're truly doing is we're learning a ranking method to predict new SemRep connections. Now, what we've shown in our prior work with Molier, that predicting good SemRep connections correlates pretty directly with predicting new hypotheses. But with lack of a better ground truth annotated data set, that's what we've got. There's no database of hypotheses, for instance.
Okay, that's great. All right, I think they got their answer.
Cool. Thanks for the questions.
Let me see if there are any more questions. It doesn't seem like there are more questions. Okay.
Cool.
With that, I would like to thank you so much for accepting our invitation, and thank you for your great presentation. Hope we see you again on this platform. Thanks everybody for joining us. Have a great day. Stay safe.
Yeah, stay healthy.